So it turns out that the previous algorithm outputs a minimum cut set with probability at least 2 divided by n times n minus 1. Now, at first you might look at this result and ask, what good is that? The algorithm doesn't even promise to be right more often than not. The trick is that we can call the algorithm multiple times and just take the minimum of these results. If we do this roughly n squared times the log of 1 over epsilon times, then there's a 1 minus epsilon chance that we will have found the minimum cut set. The proof for this corollary is that each call to the algorithm is independent. So the probability that all the calls failed is given by this expression here. Then in general, 1 minus x is at most e to the minus x. So applying that quantity to this case here, we have that the n minus 1, and the 2 factors cancel, leaving us with this expression here, which then just simplifies to the quantity epsilon. So the probability that all the iterations fail is at most epsilon. This bound here, by the way, is extremely useful in analysis, and is one you should always have handy in your mental toolbox. So then, we have that if this theorem is true, we can boost it up into an effective algorithm just by repeating it. But why is this theorem true? Consider a minimum cut set C, and we'll let EI be the event that the edge chosen in the ith iteration is not in C. Note that there could be other minimum cut sets as well, but we're going to focus on just one of them, which we're going to call C. Returning the cut set C means not picking an edge in C in each iteration. So it's the intersection of all the events EI, which we can turn into this product as we've done before. We're just conditioning the probability of avoiding C in the ith iteration, given that we've avoided it in all previous ones. Actually, that quantity will be a little easier to analyze if we write it like this. And I claim that this is at most n minus j minus 2 divided by n minus j. We'll warm up just by considering the probability of E1, that is, of avoiding the cut in the first iteration as we choose an edge. Letting k be the size of the cut, we have that every vertex must have degree at least k. Otherwise, the edges incident on a smaller degree vertex would be a smaller cut set. This then implies that the total number of edges is at least n times k over 2. Every vertex must have degree at least k, and summing up the degrees for every vertex counts every edge exactly twice. Therefore, the probability of avoiding the cut set in the first iteration is 1 minus the size of C divided by the overall number of edges. This is at least this expression here, which then simplifies to n minus 2 over n. The more general argument will be similar. Given that the first j edges chosen were not in C, then C is still a minimum cut set for the current graph. If not, then taking the edges in the smaller cut would also be a smaller cut for the original graph. And note throughout as we count edges, we're always counting the parallel ones. So again, we can let k be equal to the size of this set C, and we have that there have to be at least k times n minus j over 2 edges left. The n minus j now comes from the fact that there are only n minus j vertices left after the j iterations. With the same argument as before, we have that the probability of avoiding C in the j plus 1th iteration, given that no edges in C have been chosen yet, is at least n minus j minus 2 over n minus j, which was what we were trying to show. Substituting this into our expression here, we have that we're down to a 1/3 probability in the last iteration, 2 over 4 in the iteration before that, etc. This product telescopes and leaves us with the bound of 2 divided by n times n minus 1, which was what we were trying to show. Altogether then, this extremely simple procedure has given us a fairly efficient algorithm for finding a minimum cut set.